So what I'm planning to cover is first the sort of higher level part of how to decide whether to containerize or not, the arguments I'm aware of. And then I'm going to go more into the how-tos, best practices, things like that. Not necessarily super tied to Docker, but sort of in that area. And then I'm going to go into the more, let's say, lower level stuff, bugs that I've seen and things like that. So what I'm not going to cover is things like what Docker is, how it works, Docker run commands, running with the official image, things like that. If you're here for that, I'm sorry. But my colleague Rafa and I did a session on that last year, so you can look up the video. And I hope you still find this stuff interesting, because I think it kind of fills the gap. So to give you an idea of the angle from which I'm coming, most of the higher level stuff will come from our own process of putting stuff into containers. And the more lower level stuff is coming from mostly from our consulting and support engagements where we found quite interesting issues. So with that, I'm going to start with a little story of when we discussed Dockerizing our own environments, because the whole discussion started with a bit of a ping pong in the sense of, what does Docker bring us? And it was like, oh, but you can have the same thing on your laptop as you have in production. Well, that's not necessarily a Docker thing. I mean, you can do that with Vagrant or whatever other things that we tried and didn't really take off internally. And the discussion was kind of going nowhere until one of my colleagues, who I really respect and is a very clever guy, came up with this argument, which I found really funny and very sad at the same time. Like, is this, there's really no substance to this? And that was actually a breaking point in the sense that we started to have a more constructive discussion, and I'm going to go over the things that we actually found out that are interesting. But looking back, it actually made quite a bit of sense. Maybe not with these words, but I think if people kind of buy into a certain technology, are excited by it, then you get a lot more chances to have traction. So even if you can do the same thing, in terms of having the same thing on your laptop with Vagrant, if people hate Vagrant but love Docker, then go with Docker. So I'm used to ignoring this sort of arguments, but because they're non-technical, but I think they have their validity. So let me move to the more technical arguments. One, and I think the biggest for us, was the fact that we could do orchestration. So with something like Kubernetes or Docker Swarm. I think for us it's going to be Kubernetes. And that makes a lot of sense, especially if you're running stuff on your own data center, because then you can allocate resources dynamically. In the cloud, it's not that much in terms of, because in the cloud, you can normally choose an instance size that kind of works. But even there, if you're thinking about pricing, at least I have a few customers who claim that they get a lot better deals by having huge machines and then using containers to allocate resources dynamically on them, things like reserved instances and whatnot. But the win for us, because we're running on AWS, is that we can do orchestration without being tied to the provider's autoscaling. So with that, let me give you a bit of a demo on Kubernetes. It's not going to be like a full sort of production thing. It's going to be more of a proof of concept. So and you can find all the stuff that I'm typing here. It's there on GitHub, so you can look it up and play with it later. And so I have this. I'm not sure if you can see. I think it's fine, huh? Especially on that monitor. No. Well, it used to work. Anyway, I know. What if I move this a bit? Low-tech solutions. OK. So So I have this little Kubernetes cluster. There's this app called Minikube that you can spin up your local one-node Kubernetes cluster. And so I'm gonna do a Solr cloud setup. I'm gonna start Zookeeper, Solr, and then I'm gonna scale out Solr to 2 instances using Kubernetes. So the files I have here, besides my notes, are all some, let's say, configuration files. So let's start with this Zookeeper controller. This tells it what pods to start, and pods in Kubernetes are it can be 1 or more containers. In this case, with Solr and Zookeeper, I'm going to have 1 container per pod, so that's like an entity of work. And this controller tells it basically to spin 1 instance of Zookeeper with this Zookeeper container and expose port 2181. So I'm going to go ahead and start it. And now if I do get pods, I will see my Zookeeper node has started. Now, if I want to access this from Solr or from my own terminal, then I need to expose this as a service. And this is what Zookeeper service is about. So I'm just going to forward basically this 2181 port and expose it as Zookeeper service. So, hello, what's with you? Anyway. So now I can do get services, and this is the port on which Zookeeper now can be accessed on. So I can say, I'm going to save this in an environment variable, zk port. And I'm going to also save the host, which is, in this case, is I have only 1 node, it's that node's IP. But to show you, I'm going to upload the Solr config, right, to this Zookeeper to show that it works, or hopefully it works. Okay, so now I have the config set in Zookeeper. And now I'm going to do the same with Solr. So the Solr controller, this again tells it to start 1 Solr node. And it's going to use the official Solr image. And I'm going to, again, expose port 8983. And I'm going to point it to our Zookeeper service. So the official Solr image is smart enough that if you pass this environment variable, it's going to modify solr.in.sh so that it starts Solr pointing to Zookeeper. Let me copy paste because it's safer. All right, so now if I do get pods, there's my Solr pod in addition to the Zookeeper pod. So now hopefully it's going to work with, I'm going to create a service which does the same thing as you saw with the Zookeeper service. Just basically forwards the port, 8983. So now if I do get services again, this is my Solr port. So let me connect to Solr to see that it works. It's a different port each time. Yeah, I have Solr. And sure enough, I'm not sure if you can see that, but it is pointed to my Zookeeper service. And I can actually see if I go to cloud, I can see the config that I just uploaded. All right, so now let's say I add more hardware to this cluster, and I want to add more Solr nodes. So I'll just need to modify this replicas, which was configured to 1 to give me 1 Solr node. I modify this to 2, and this will spin up another Solr node. Of course, this is just an example. Normally, you will have rules in terms of how to place nodes and things like that, but by and large. So if I do get pods again, you can see now I have 2 Solr pods. And I should be able to see this in here, not graph because I have no collection yet. But I can see this with live nodes. I have 2 nodes right now. And just to finish it up, so to speak, I'm going to create a collection with 2 shards. Port refute, huh? I didn't save the Solr host, Solr port. So Solr host is, again, my IP. And Solr port is this guy here from Solr service. Okay, so now hopefully it's slow, but it's working. Is it? Is it? Yay! Oh, I have it on 2 nodes. Okay, so let's just index a couple of documents and do a search, and then we're done. All right. I mean, a couple of the same documents. That's good enough. And let me do a commit. All right, so now I should be able to do a search and show those documents. Sure enough, they're there, and they're also distributed to shards. Shard 1. I have some on one shard, some on the other, so everything seems to work as expected, so to speak. All right. So let me move on to some other things, some other conclusions that we came to. So one is this thing about having the same thing on your laptop as in testing, as in production. The differences, I think, with containers compared to VM-based solutions is that containers are, those images are lighter, they're easier to download. And the fact that the Docker is the future, so there's a lot of community, a lot of hype around it. You can find a lot of software that's already there. You don't need to install or anything like that. You just pull up the container and start it. And of course, it starts quicker and things like that. And also, when it comes to development, this becomes also an efficiency problem because it's a Docker image is gonna, a Docker container is gonna be lighter. But actually, if you're running on a Mac, you have a Linux VM, so not that great. Now let me move on to the middle part, to the how-tos. In this demo, I only had 1 zookeeper, but normally you have more, and you'll also need to make sure that they're hosted on different hosts, so that one going down will not kill everything. In Kubernetes, you can do that with something called pod anti-affinity. And more of the same applies to Solr, right? You don't want to, normally you would want to balance how many Solr nodes you allocate to the host you have. And the same applies to allocating shards of a collection or shards in general to have your Solr cluster balanced. And the way to do that in terms of scaling strategies, you can have more shards per collection initially, and so that you can add nodes and then rebalance them and still have a balanced Solr cluster. And if you have time series data, I think a good practice is to have time-based collections. So let's say, not time-based, actually size-based collections. So when you get to, let's say, 5 gigabytes per shard, you're going to create a new collection and you're going to index there. And so this allows you to decide at every point you create a new collection. If now you have more nodes, you can create a new collection with more nodes, with more shards. And so you're scaling up indexing that way. And also deletion is going to be much more efficient because you're going to delete complete collections. And also caches are going to work better because collections that are no longer written to caches will live a lot longer. Now let me move on to the underlying, let's say, storage and operating system stuff behind Solr. One thing that has to do with Docker here is to use volumes. So normally the disk stuff isn't persisted. The mounts aren't persisted with Docker, so you need to use volumes. In the case of Kubernetes, there's a concept called stateful set, which is a bit more than just using volumes. Of course, you need to make sure that the Solr process has access to those, in terms of permissions, to that data. And in terms of performance, of course, local disks will be faster than network-based solutions. But if you do go for network-based solutions, for example, in AWS to use EBS, then it's good to have them on a separate network card than your main network stuff. So in this case, you would use EBS optimized to make the regular network latency acceptable, so that you don't get zookeeper timeouts and things like that. That would be pretty tragic. Yeah, in AWS, you can also make sure that your instances have enhanced networking. So this is a driver thing. It's not something you need to pay for, but it gets you really much more consistent network performance. Now, one question that comes up quite frequently is whether to have big or small hosts. Now that you're containerizing and you can dynamically allocate containers, how to go with it. I think if you have small hosts so that you have one container per host, you lose quite a lot of the advantages that come with co-locating multiple containers on a host. For example, the operating system caches part, that is managed separately than the container memory. So those are shared. So if you may, for example, co-locate Solr with something that doesn't use I/O that much, and then Solr will be able to use the whole remaining memory, as opposed to running those other containers on a separate host and then having some free memory that's not used. But if you have hosts that are too big, then you're likely to run into issues that I'm going to talk a bit about in terms of memory allocation. I don't think the whole ecosystem is really ready to use very big hosting, terabytes of RAM and things like that. And also, if one of those giant hosts goes down, then that's going to be much more disruptive. And the same question applies to whether you should have big or small Solr nodes. But I think the rule of thumb here is to have them as big as they can comfortably be, in the sense that if you have many small nodes that will require many small shards, and that will have overhead, and it's going to be more difficult to manage. Zookeeper, the cluster state will be bigger and things like that. I wouldn't worry so much about things that are single-threaded, such as full-text search or facets, because normally they get naturally parallelized between either multiple requests or multiple shards that you hit in a single request. Indexing is definitely multi-threaded, so that can usually uses up all the CPU if it's needed. And I mean, for facets, if you use the regular facets, so not the JSON ones, you can also set facet.threads. But when I say how comfortably big they can be, I mean not too big so that you have like two Solr nodes and one goes down and then you're in trouble. But also, if you have multiple nodes, they can't be too big because you cannot allocate an unlimited amount of heap to them, even though you may have a lot of memory. So let me talk a bit about heap. I think the heap requirement will mainly be influenced by how much data you have, but also on how much how expensive your requests are, so that sort of transient memory. So the more data you have, the more, let's say, static data structures, such as pointers to the terms dictionary, doc values, those will take more memory. And then with that also caches will take more memory, but of course that depends more on your cache configuration. So a rule of thumb for me at least is to start with, let's say, you just start Solr, it loads up the indices, you see how much memory it takes, and then you add, let's say, 100% more as some headroom for your requests, but also for the garbage collector to be able to go up and down. And of course, you cannot allocate too much memory to get close to the host limit. So if you have, let's say, 60 gigs of RAM, 64, let's say, you don't want to have two 30-gig heaps there, because then you don't have enough room for operating system caches. And there also, as the heap grows with your data and your requests, I think there are some issues to be considered. One of them is that at 32 gigs, the JVM loses the ability to compress pointers. So there's an overhead then in terms of usable heap, which again will depend on your use case. You can do a heap dump and see how many objects are actually there. So that gives you an idea of how many pointers you would have, and so the overhead. Usually a good rule of thumb, I think, would be like 5 to 10% overhead if you go beyond 32 GB. I would also actually keep it under, assuming we're on Linux, I would keep it under 30 GB, because after that, even though you're under 32, the pointers are compressed, but they're not aligned to the virtual address 0. So the CPU will have to do more cycles to access those addresses. So yeah, like 30 GB would be, I think, a hop. Beyond that, I would think about garbage collection. If the garbage collector is fast enough to give me the throughput I need and also the latency. But this 32 GB problem, let's call it, will create basically a hump. So you either have it under 30 GB, is what I would say, or over, let's say, 45. Because otherwise, if you have like 35, it's probably, you might as well have 30. I think you can even go over 100 gigs with a single node, but I think that's a bit of a stretch. But beyond those 45 GB, I think I would obviously measure and see if garbage collection is a problem. My experience is that sometimes it happens that the default settings, which are good enough for most use cases under 30 GB, the default settings tend, sometimes I see that it just doesn't have the necessary throughput, so you sometimes may get out-of-memory errors. But more often, there are latency issues. So there's too much pressure on the garbage collector, so collecting that garbage takes too long, and you have pauses, and then it disconnects from Zookeeper and all that stuff. And usually this stems from premature moving of objects from the new generation to the old generation. So if that's the case, then the solution is to increase a bit the Eden and Survivor. And also you can make the old GC, the CMS, to kick in earlier to have a bit more headroom by lowering the initiancy occupancy fraction. One thing that is scary for some people is to use G1 with those large heaps, because some recommend not to use G1 with Lucene and Lucene-based search engines. I personally had really good experiences with G1. It has some overhead in terms of heap, because the way it works basically for the old generation, because for the new generation it's the same, is that it has some regions that it tries to divide in, I think, 2048 regions or something like that. And you can also configure the region size, and it moves objects around from one region to another and removes regions. So that also means it compacts heap, which CMS doesn't do. And also the thing I mentioned about making the young generation bigger if needed, this is something that G1 does automatically. So you give it a target pause time, and then it sees how much garbage collection actually takes, and if it takes longer, then it tries to adapt those sizes to meet those goals. So of course, if you have a large heap, you don't want to have a very small pause time because that will make it pretty much go crazy. You need to be reasonable, so to speak. If you want to read more about garbage collection, I think that's a really good page to start on, the wiki that was written by Sean, and then it has a lot of references to a lot of concepts that I think are very interesting. Let's go back into a more, let's say, Docker territory, as normally you would have more than one node per host. One thing to look for is the number of threads, because before Java 9, most defaults have to do with the number of cores that the host has, and not the number of cores that you set for the container as a limit. And so those threads can be garbage collection related, or can be facet threads. Those you would configure manually anyway, but also merge threads, because those are usually automatically set according to the total number of cores. Though with merges, and my colleague Rafał did a talk on those with optimize and all that. If you're running, those also depend on I/O. So if you're running on SSDs, you probably want to have one merge thread per node. But if you're running on really fast SSDs, then the problem is shifted back to CPU. So you're, again, back to deciding how many threads you want per container, and not regarding the overall CPU. With Java 9, it's going to be smarter. It's going to figure out that it's running in a container, and it has that many CPUs. Now, speaking of container limits, with memory, I mentioned that operating system caches are managed separately. So you normally, let's say if you have a heap of 30 gigs, you normally allocate something like 40 to give it some headroom for the other stuff. But you don't need to include the operating system caches in that container limit, because this isn't accounted for. And that would be confusing, because it can go then much further. One thing about CPU, because normally you would give it a percentage or something like how many CPU shares to give to a certain container. So let's say 20% of the host's CPU. The problem with that is if you're running on a host that has multiple NUMA nodes. So those are typically on a multiprocessor, physical machine. The point is, for a specific processor, you have a region of memory that's accessed faster than the other regions which belong to other processors. And Docker isn't aware of that. So you can end up with a Solr node that has some threads running on one processor, some threads on another processor, and then they access across the nodes, and that's going to be slower. So one way is to just rely on the kernel, which should theoretically balance those threads so that threads of the same processor of the same process end up on the same NUMA node. But you can also use CPU set to pin a specific container to let's say core 0, core 1, core 2, something like that. The same applies to operating system caches. By default, if operating system caches fill up the memory of one node, then you will prefer allocating caches to another node, even if it has to go across nodes, than to hit the disk, which may or not be the best thing. I haven't tested it. I guess it will also depend on the use case, but you can configure that with the system option, zone reclaim mode, which can make it reclaim least recently used caches from the current node in order to allocate the new ones there. One really interesting bug that I've encountered is, which goes back to Java 7 update 80. That was actually the last version where it worked. And it was fixed in May this year or something like that, really recently. So unless you have a very, very recent Java version, you're very likely to be hit by this bug. Basically, on all busy mmap systems, which Solr is typically, if you map and unmap because segments are merged and things like that, then those operating system caches aren't actually given back to the operating system, and instead they are mapped as if they belong to the process. So what you see is the RSS is growing. So like if you do a free, you will see the used memory growing and the cached memory shrinking until eventually the host runs out of memory, and then the OM killer kicks in. And actually, the thing about the OM killer, it doesn't necessarily kill the app that requests memory, because it has no clue, which app has a memory leak. It will give scores depending on mostly how much memory is being used, and so that's why typically Solr gets killed, even if sometimes it may not be Solr's fault. If you encounter situations like this, one option that I find interesting for debugging is native memory tracking. You can see, like over time, it's going to add some overhead, of course, but you'll have a detailed log of how much memory is going to be allocated. And there are also some other things that I find that are good practices. Of course, one of them is not to overbook memory. So if you have like 128 gigs, you don't want to have 5 nodes with 30 gigs each, because you can, because the operating system will gladly tell Solr, sure, here's 30 gigs of heap, but it doesn't actually allocate it until it's needed. So you can start those 5 containers and figure out down the road that some of them started to be killed by the OM killer. So you probably want in that situation to have, let's say, 2 nodes of 30 gigs each, and that will give 60 gigs for OS caches, and that should be fine. And if you do that, then you will also probably want to use always pre-touch, which will zero out the memory that gets allocated, and that actually allocates that memory. It doesn't only get a promise, and that also ensures that that memory isn't fragmented. Another system option is minimum 3 kilobytes. This is kernel's, let's say, reserve, which defaults to 64 megabytes. So if you have a host with like 2 terabytes, it's very likely that that's too small. So some other stuff that I find interesting in this area is that not only the JVM has bugs in this sort of setup, but of course Docker is also young technology. It's also full of interesting stuff. But also the kernel, which you would say, okay, it's a mature piece of software. Well, it is, but not necessarily in this setup with the whole, huge machines or with C groups. This is, a feature that's been for a while, but not so much used that as it is now. You need to make sure that each process is able to have enough open files and to lock enough memory, of course. If there are issues, if you have bugs, the place that I look pretty much the first is dmessage. So you'll see, if there's an OM killer or something like that, you see very detailed stuff about what happens, including like how, if an OM killer is triggered, you will see what process allocated how much memory, because you see order 0, order 1. That's how the power of like how many pages it requested. So if it's order 0, it's 1 page of 4 kilobytes. Another thing that I find interesting is if you look at top and you see the kswapd process going to like 100%. That process is, let's say, the kernel's garbage collector, which runs on a single thread, wakes up when there's not enough memory, it needs to reclaim something really quickly. So if that's 100%, it's a sign of a problem. It's a sign that the kernel cannot allocate and deallocate fast enough. So the solution for that, I don't really know. It depends on the situation. The obvious one is to use smaller hosts or virtual machines. But I would also bring up a few things that I didn't really test yet. One would be if NIOFS becomes a solution now, because with mmap you do a lot of allocation and deallocation of data. With NIOFS, probably not. So NIOFS is typically slower than mmap, so that's why it's not so much used. But if you think about allocation and deallocation, there's this transaction look-aside buffer, which is CPU's cache of knowing where each page is allocated. So if you thrash that too much, then you lose performance. So I'm not sure if it's actually faster in these sort of extreme situations. It's also, I think, debatable whether absolutely no swap is a good idea, especially in the case of Docker, where you can configure per container whether you want the container to be swapped or not. So for Solr, yeah, sure, you don't want to swap the JVM heap, but maybe you want to swap the memory of some other process that you have running on the same host, or maybe you want to swap, let's say, our syslog that's running on the host's operating system, right? That may not be such a big of a deal. With mmap, there's this interesting concept of mmap arenas. So the kernel does this optimization where when you request to access a file and it needs to allocate that virtual memory, it's not like a big blob of memory. It divides it into arenas and it tries to have smaller manageable chunks. And you have more arenas, the more memory you have. And so there's a trade-off here between, if you have many small arenas, it's going to be cheaper to allocate and deallocate, but it may find that some arena's full and needs to try again. And this is actually something that amplified the bug that I talked about earlier on with mmap, because if you have many arenas, then it will try in different places and it will be locked in all that places, so the leak is running faster. There's another thing that's usually not recommended to be used with big data systems, such as Solr, which is transparent huge pages. So what huge pages are, normally a page is 4 kilobytes, right? So if you have a lot of memory, it's very difficult to keep track of all the addresses. So huge pages, which is disabled by default, makes pages of, let's say, 2 megabytes. And so that will make this transaction look-aside buffer be more efficient in terms of looking at pages. The downside is if you want to access, let's say, a segment that's 10 kilobytes, you're going to have to read 2 megabytes instead and cherry pick those 10 kilobytes. So again, I think it's a trade-off here that may be worth looking at. If you want to learn more about Linux memory management, there's that site, linuxmm.org. I find it's kind of old school and in terms of how it looks and how it's written, but there's a lot of information there, and I'm quite amazed about how little things I know about memory allocation. So that's pretty much all I have. I'm just going to do a quick recap. I think I like orchestration. I'm very excited about Kubernetes. And I like the fact that operating system caches are shared between containers. I think that's also a thing that we can take advantage of. And it might actually get a lot of traction sort of internally, especially in our company when it comes to getting people involved and having really that thing with the same environment from development to production. Thing is, when you automate, you obviously need to get things right. You're not having those 2 nodes that you can just SSH into and fix things on the fly. So yeah, then that's a challenge, I think. And also a challenge is, I guess, the ecosystem, which is still young, still has those bugs, those things that will need to be ironed out. But I think it's, overall is a doable thing, I would assume. So thank you very much. If you have time during the break, please visit our booth. We're also hiring, and feel free to reach out via Twitter, email, everything. Yeah.